Modern cars are no longer just metal and pistons. Every component operates close to its material limits, thinner, lighter, and more sensitive than ever before. That's why many vehicles stop at 100,000 miles while others keep going strong up to 500,000. The difference isn't luck. Combustion pressure, temperature, and friction all interact to determine engine lifespan. In this video, we'll break down each underlying mechanism to show how an everyday user can extend engine life without major repairs. Reality: why cars fail early. To reach the 500,000 mile mark, you first need to understand one thing: why most modern cars fail so early. This isn't random, it's the result of a series of small deviations accumulating over time. In the repair industry, the 150,000 to 200,000 mile range is often considered the red zone for poorly maintained vehicles. When failure happens, the costs are clear. Engine $10,000 to $18,000, transmission $2,000 to $8,000. The cause is not a single fault, but a chain of systemic issues. Poor maintenance, delayed oil changes, using the wrong oil grade, or neglecting oil level checks. Over time, the oil loses its lubricating properties, sludge builds up, and narrow oil passages gradually become restricted. Metal components begin to experience friction without adequate protection, operating under stress, accelerating immediately when the engine is still cold, shutting the engine off abruptly after heavy load. These create unstable cycles of temperature and pressure, ignoring warning signs, unusual noises, slight vibrations, warning lights. The system slowly drifts away from its stable state. As a Bosch engineer once said, major failures don't happen in a single day. They are the result of thousands of small operational deviations. A car doesn't fail randomly, it reflects how it has been used. Understanding this chain of degradation is the first step. In the next section, we'll dive into the 4 fundamental mechanical pillars, the principles that determine whether a car fails early or reaches 500,000 miles without a major overhaul. Pillar 1. Oil management, the 3-stage filtration system. Inside an engine, no component bears load as directly as metal, and no protective layer is more critical than engine oil. But to reach 500,000 miles, you have to stop treating oil changes as a routine task and start seeing them as friction management at the molecular level. Every internal movement relies on an ultra-thin oil film to maintain separation between surfaces. This film exists due to pressure and viscosity. When stable friction is controlled, when it weakens metal-to-metal contact, begins and where starts from that very moment. These particles don't disappear, they continue to circulate through the system, passing through extremely tight clearances, creating microscopic scratches on metal surfaces. This process is slow, almost imperceptible, but over tens of thousands of miles it accumulates into real wear. This is where standard oil change intervals become inadequate. The 7,000 to 10,000 mile range is designed to optimize short-term cost, not to maximize mechanical longevity. If long-term durability is the goal, the approach must change. Maintain oil change intervals within 3,000 to 5,000 miles. Use a high-quality oil filter capable of capturing fine particles down to 20 microns. Ensure the system is always operating with oil that remains in a stable condition. At the microscopic level, even a small amount of wear particles repeated over time can alter the entire working surface of components. Economically, the difference is clear. An oil change costs around $60. Even when maintained consistently over a long lifespan, the total cost remains far lower than $12,000 for a new engine. As one technician put it simply, engine oil is the cheapest thing in a car, but it protects the most expensive. And that is the first foundation. If oil is not under control, everything that follows loses its meaning. Pillar 2. The fluid renewal cycle of the drivetrain system. There's a concept that sounds very safe, but causes major misunderstanding in engineering lifetime fluid. It sounds reasonable, but in mechanical systems, no fluid retains its properties after tens of thousands of miles in operation. What's really happening inside the transmission and differential rely on gears and friction surfaces under constant load. Even with lubrication, this process generates extremely fine metal particles during every operating cycle. At first, the amount is negligible, but if the fluid isn't changed, these particles gradually accumulate within the system. The problem is, these metal particles don't stay still. They continue to circulate with the fluid passing through extremely tight clearances, especially in the valve body, the component responsible for pressure control and gear shifting in automatic transmissions. As contamination builds up, control valves begin to stick. Hydraulic pressure becomes unstable. Shifts become harsh, delayed, or incorrect. This is the stage where many people believe the transmission is starting to fail. But in reality, the wear process began long before that. Many manufacturers advertise transmission fluid as lifetime, requiring no replacement. But an engineering lifetime does not mean forever. It usually corresponds only to the warranty period or a standard usage cycle. If the goal is 500,000 miles not changing, the fluid means allowing metal particles to accumulate without control. To keep the system stable, you should perform a drain and fill every 30,000 to 40,000 miles. Ensure the fluid remains clean and capable of proper lubrication. This doesn't reset the system. It prevents the internal environment from becoming a source of wear. One well-known case is the Toyota Tundra reaching 1 million miles. The common factor wasn't a special design, but consistent annual changes of differential and transmission fluid, regardless of lifetime fluid claims from the manufacturer. The result didn't come from a major upgrade, but from controlling small factors repeated consistent and precise. A transmission doesn't fail from a single use. It fails when accumulated metal debris exceeds the system's control threshold. Fluid renewal isn't advanced maintenance. It's how you prevent the system from slowly destroying itself. Friction is only part of the problem. Another factor silently affects the entire system, especially plastic and rubber components. Once it crosses a threshold, degradation can accelerate faster than you expect. Pillar 3. Local thermal management. The cooling system. Not all failures come from friction. A large portion comes from how heat is managed or mismanaged inside the engine. Modern engines are designed to operate steadily within the 90 to 105 degrees Celsius range. The entire thermal balance depends on the cooling system functioning precisely. But this very system contains inherent weak points. To reduce weight and cost, many components such as coolant hoses, connectors, water pump housings, and thermostat housings are made from engineered plastics and synthetic rubber. Under long-term operation, these materials are constantly exposed to heat cycles, expanding when hot, contracting when cold. After around 100,000 miles, material aging becomes noticeable. Rubber loses its elasticity, plastics become brittle and prone to cracking. These changes weaken the system's ability to maintain pressure. When even a small component in the cooling system fails, such as a cracked hose or a weakening water pump, temperature can spike within minutes. It only takes a minor loss of sealing like a leaking hose or a worn pump seal for system pressure to drop rapidly. When that happens, the boiling point decreases and the coolant loses its ability to dissipate heat. Temperature rises quickly, not gradually. At high temperatures, metal expands beyond tolerance. The cylinder head can warp. The head gasket can lose its sealing capability. This type of failure doesn't accumulate slowly like wear. It happens fast and the damage is often irreversible. To avoid this breaking point, the approach must shift from reactive to proactive. Replace rubber hoses, the water pump, and critical plastic components around the 150,000 mile mark. Inspect the cooling system regularly, especially for small leaks or signs of pressure loss. This isn't repair, it's prevention before failure occurs. This system doesn't fail gradually, it remains stable until it crosses a threshold. And when that happens, you have minutes to react, not thousands of miles. Managing this well eliminates one of the fastest causes of engine failure. But this still isn't the end. There is another factor that ultimately determines the lifespan of the entire system. Pillar 4. Combustion chamber and intake system cleaning, decarbonization. If the first 3 pillars protect the physical structure, this final one protects the soul of performance. Modern GDI engines have a subtle but critical weakness. Internal buildup can gradually choke performance if not addressed periodically. Gasoline direct injection. GDI engines achieve high efficiency by injecting fuel directly into the combustion chamber, but this very design removes a natural self-cleaning mechanism. In older engines, fuel passes over the intake valves, helping wash away deposits. In GDI systems, the intake valves no longer receive that cleaning effect. Over time, oil vapors from the ventilation system and combustion byproducts stick to the surfaces of intake valves and intake ports. This carbon layer becomes thicker and harder, reducing airflow, disrupting intake dynamics, and lowering compression efficiency. At more severe levels, it can lead to pre-ignition and abnormal vibrations. For mechanics, the intake system is like the lungs of the engine, and carbon buildup is a slow but continuous form of clogging. A common solution is walnut blasting, using crushed walnut shells to clean valve surfaces. It's abrasive enough to remove hardened carbon, yet gentle enough not to damage the metal. Recommended interval about every 50,000 miles to maintain stable airflow. A typical case, a 2019 Audi A4 with only around 35,000 miles, began showing throttle hesitation and slight vibration at low speeds. There was no obvious mechanical fault. The cause carbon buildup in the intake and on the valves. After walnut blasting, throttle response returned to normal and the engine ran noticeably smoother. Periodic cleaning isn't about increasing power, it's about restoring the engine to its original operating condition. The 4 technical pillars we've covered form the hardware of a 500,000-mile system. The rest depends on how you use the car. The secret of operation. This is the part that determines how the entire system is activated every day. An engine can be perfectly maintained, but its true lifespan is decided in very short moments, especially right after startup. Most engine wear occurs within the first 60 seconds. At this point, the oil is still sitting and the oil pan pressure hasn't stabilized, and metal surfaces are not yet fully lubricated. The system is in a not yet ready state. The proper operating principle is let the engine idle for about 20 to 30 seconds. Then start moving gently, keeping RPM low. Avoid hard acceleration until the temperature stabilizes. You don't need to wait for the engine to fully warm up before driving, but applying heavy load too early is the fastest way to create permanent wear on crankshaft and camshaft bearings. Oil pressure increases with RPM, but lubrication effectiveness depends on temperature. When the engine is cold, the oil is thicker and struggles to flow through extremely tight clearances. At the same time, metal components haven't yet expanded to their designed tolerances. If load is applied suddenly, forces are distributed unevenly across the system. These habits will shorten your engine's lifespan. Accelerating hard right after startup high load before the system stabilizes. Shutting the engine off immediately after aggressive driving oil stops circulating, while heat remains high, allowing deposits to form in the turbo. Overusing start-stop in heavy traffic, repeated restarts under suboptimal conditions, increase wear during the most vulnerable phase. An engine doesn't fail because of a single mistake. It fails because of small actions repeated every day. The difference between 100,000 and 500,000 miles is not technology. It's how you operate the vehicle in the moments most people overlook. A car doesn't reach 500,000 miles because it's inherently more durable. It gets there because its owner chooses to spend on maintenance, not repairs. No car is naturally long-lasting. Only systems that are operated correctly, repeated consistently over time. Where is your car right now? Comment your maintenance approach. Let's optimize together. Subscribe so you don't miss the core principles. Cars don't fail suddenly. They fail when you stop paying attention.